Chapter 18, Nutrition and Metabolism. So just for some basic definitions, nutrition is the food, vitamins, and minerals that are ingested and then assimilated into the body. So that means that it's the stuff that we ingest and then are able to use to help our body function and grow properly. Metabolism is the process of actually using those food molecules as energy sources so that we can use them as building blocks for our own molecules. Catabolism is the process that breaks down food molecules, releasing their stores of energy, and oxygen is an essential nutrient in catabolism. So catabolism is breaking it down so we can use it. Anabolism is the process that builds food molecules into complex compounds. So what that means is that it's taking those food molecules after they've been catabolized and broken down to that smaller molecular level and then rebuilding them as more complex chemical compounds that our body needs them as. So I normally had a hard time when I was originally learning this, deciding or trying to differentiate which one was breaking it down and which one was building it up. The thing that finally ended up kind of making me remember it, just those stupid things that help you remember, was catabolism starts with cat. And I don't know if any of you have cats, but when I was going through my original undergrad, had a very wild kitten who would destroy everything. When I first got him, he pretty much broke everything that was breakable in my house. So I remembered catabolism because my cat broke everything. So cats break things. And then anabolism kind of made me think of an ant, and ants are so organized in rebuilding things. So that's how I remembered those. So metabolic functions of the liver. We're just going to start there because the liver is so important for metabolic functions, and because if you remember from hepatic circulation, all of our blood flow that leaves our GI system immediately filters through the liver. So it's very important, plus it comes in really early. So the process, the liver processes blood immediately after it leaves the GI tract. That you should remember from hepatic circulation. And your liver helps to maintain a normal blood glucose level. This is also the site where both proteins and fats are metabolized. And if you remember from hepatic circulation, your liver is also really important in removing toxins from your blood. And that's why people always say that your liver is so important for alcohol, and it's because alcohol is really a toxin, and your liver has to metabolize it and get it out of your blood. So for overall nutrient metabolism, start with carbohydrates because they're super important since they're our body's main source of energy. Carbohydrates are the preferred energy food for the body, and that's just because carbohydrates produce more energy per mole of carbohydrate. So mole is just like a chemical weight measurement. It's just what you use when you're measuring very small, like micronutrients, and carbohydrates just produce a ton of energy per mole. So that's why it's the preferred energy source, especially where it's also very easily broken down. We don't have to transfer it into another type of molecule before we can use it. So it produces a lot, and it basically comes in this pre-made form. So carbohydrates are primarily catabolized for energy, but there are a few very small amounts that are anabolized. So remember, catabolized breaks down, anabolized builds up by glyconeogenesis. And this occurs in the liver cells, and that's because that's where we need to store glycogen, because glycogen works as our backup glucose level. So if we don't have any glucose circulating in our system at a time when we need energy, we can break down that glycogen that's stored in our liver to produce glucose that we can then use. So energy is transferred by ATP. ATP is just an abbreviation. You don't need to know what it stands for, but it's sort of like the body's energy unit. So we can make different things into ATP, but ATP is what we actually use for energy. And the amount is different based on the different type of food that it is. So ATP isn't stored. We make it as we need it, and it's used up almost instantly. And so it's used and then put directly into cellular work. So blood glucose is basically just the amount of glucose that we have in our blood. Glucose is just like a very basic form of sugar. And it normally, in an average healthy person who's not suffering from any type of insulin deficiency, or if it's not directly after a meal, should have a blood sugar of between 80 and 110. And that's per 100 milliliters of blood, but that's kind of the average measurement that you would get. But when we take a sample of somebody's blood, we kind of calculate out that. So if you take a sample of somebody's blood, if they were fasting, hadn't just had a meal, you'd want their blood sugar to be between 80 and 110. Insulin accelerates the movement of glucose out of the blood and into the cells. So therefore it decreases blood glucose and increases glucose catabolism. So if I have glucose, what it's going to do is pull that glucose out of the blood because it's helping me break it down so I can use it to make ATP. Remember how I said ATP was what the body uses as an energy source. So I break down that glucose into ATP, which I can use for energy by using insulin. So then fat metabolism. So fats also work primarily as an energy food. They can be converted into glucose by catabolism, but excess fat can be anabolized to form adipose tissue. So if you can remember way back to when we were doing the integumentary system, adipose tissue is sort of this fatty layer that's located underneath your skin. And any excess fat that you don't immediately break down for energy, that's where it goes and it's stored. And then protein metabolism. Proteins are catabolized for energy only after we have completely depleted our stores of carbohydrates and fats, because we really prefer to use our proteins as building blocks for the foundations of our body to make things like our muscles or our tissue. We don't really want to use them for energy. But gluconeogenesis is a process in the body where you can break apart amino acids to convert them to glucose so that if we really have to, we can use them for energy. So then vitamins. Vitamins are an organic molecule and they are needed in very small amounts for normal metabolism. So by very small, it just means little teeny tiny microscopic amounts. And that's because while vitamins are super important, they're not really a building block. They just sort of help make things happen. So they're very vital, but we only need a tiny bit of them. So avitaminosis means a deficiency of a vitamin, and this can really lead to very severe metabolic problems because while we only need that teeny little bit of it, whatever that metabolic pathway is, it can't happen without that vitamin. So maybe you only need one serving of it, but if you don't get that one serving, that metabolic pathway can't happen. So an example of an avitaminosis would be scurvy. Scurvy means that you have a deficiency of vitamin C. And then you could also have a hypervitaminosis. This is an excess of a vitamin. So this can really be just as serious as avitaminosis because it can be pretty toxic if you get too much of a certain vitamin. And this can either be chronic or acute. So chronic would mean that you consistently take too much of something and it damages you over time, or acute would be that all of a sudden you take vastly too much of something, so that damages your body. So minerals. Minerals are inorganic molecules that are found naturally in the earth. I don't expect you know inorganic or organic or what that means. That's more of a chemistry thing than this. But minerals are also required for normal body functions, and one of the important things that they have to do is that they function for nerve conduction. So they attach themselves to enzymes to facilitate how they work. So we're just going to talk a little bit about metabolism. So for metabolism, everybody has a basal metabolic rate. And that is the rate of metabolism in a person who is lying down, but they're awake and they're comfortable. They're not trying to do anything. They're not digesting food. They're not in pain. They're not worried. They're just comfortable and content and lying down, but they're awake. They're not sleeping. and that's just your basal metabolic rate. So that means that is how many calories you burn while you're being awake, but you're not stressing your body. Now, your total metabolic rate is the total amount of energy expressed in calories. Calories is just the way that we use to calculate metabolism. It's just like another measurement. But the total amount of energy expressed in calories that is used by your body in a whole day. So the difference between those is that your basal metabolic rate, the things that affect that are more things that have to do with your body, where your total metabolic rate is going to have a lot more to do with your activities and your environment. So things that will affect your basal metabolic rate are your sex, so male or female, your age, how large or small you are, your body composition, so that means fat to muscle ratio. If I have a lot more muscle than somebody else, then I'm going to burn a lot more fat, or a lot more calories, than they will, just because those muscles take more to maintain. The amount of various hormones that are just naturally released into your body, and then just other things that will affect it a little bit. Like if you're awake, you can't totally shut off your emotions, or if you took a drug earlier that day or something like that. That'll affect your basal metabolic rate a little bit. And then your total metabolic rate, that's things like if I get up and run for 3 miles every day. That counts for my total metabolic rate. It's influencing that. So that will change that for me. If I eat very thermic food, so it just depends on like what kinds of food I eat or what environment I'm in. So like I live in Maine, freezing cold about half the year. So I'm going to burn more calories just because it's cold and my body's using them to stay warm. So that's just a little bit of the difference between a total metabolic rate and basal metabolic rate. So you can have a disruption or imbalance of metabolism that can be caused by several different factors. There are some inborn errors in metabolism, and those are normally genetic conditions that have to do with either a chronic deficit or some sort of abnormal metabolic enzyme or pathway in the body. Or you can also have some metabolic disorders that are just complications of another disorder, like a hormone imbalance. If you have a problem with your thyroid hormone, remember how your thyroid hormone, if you had too much or too little of it, tended to make you either gain or lose weight. It's because your thyroid hormone is going to trigger your metabolism. So if you have too much or too little of it, it's going to affect your just basal metabolic rate. So something else that can really affect it would be eating disorders. Because remember how what you eat and how much you eat can affect your total metabolic rate. So just for some eating disorders, most of these people probably do know, there's anorexia nervosa, and anorexia nervosa is characterized by the chronic refusal to eat. Normally there's a really big psychological component to this, as well as with bulimia. Bulimia is an alternating pattern of craving food and normally binging, and then a period of self-denial and purging. So if they purge, it's actually called bulimiorexia. And that's because they're actually getting rid of what they eat. They don't want to actually eat it. But it's that pattern of craving and then denial or guilt over it. Obesity is actually also considered an eating disorder, depending on what the symptoms are and what makes somebody be obese. Not everybody that is obese has an eating disorder, but if it comes from some sort of psychological component where it's almost like a compulsive eating that makes them be obese, then it's actually an eating disorder. And then finally, another example would be a protein-calorie malnutrition, and that results from a deficiency in calories, but in conjunction with that deficiency in calories, it's also a huge deficiency in proteins, and that really affects a lot of stuff in their body, because remember, proteins are really the main building blocks for your body. So a protein-calorie malnutrition results in a deficiency of calories in general, but in particular proteins, and oftentimes it can be a complication of some sort of pre-existing disorder. And there are sort of two different types when it starts to become more advanced. So the types of this when it becomes more advanced are marasmus, and that's when it's an overall lack of calories and proteins. And this is characterized a lot by tissue wasting and a lot of fluid and electrolytes imbalances. And then another kind would be kwashiorkor, and that is when there is a lack of proteins in the presence of sufficient calories. And it's similar to marasmus, but this one is distinguished by ascites and flanking dermatitis. So these are, if you ever watch, if you've ever seen the pictures, normally it's of kids in foreign countries, and they look like they have these teeny tiny little legs and then these great big round bellies. This is what they're suffering from. It's because they're being fed and they're trying, their parents are trying to feed them, but they just don't have protein in their diets. And without proteins, they can't build up their body tissues like they should, and results in a lot of imbalances, and that's what creates them to have those teeny tiny little extremities and then great big round bellies. So that will be an example of it. You can see how they get just great big round bellies. So this one, they can suffering from calories and proteins, and this one you can see where they have calories, but that great big round belly. So getting away a little bit from diet, we're just going to talk a little bit about body temperature, because that does have a lot to do with your metabolic rate. So your hypothalamus is really what regulates the homeostasis of body temperature throughout a variety of processes in your body. So one of the things that happens to help regulate your body temperature is your blood flow to your skin. So when you're hot, it increases, and that's because the air is almost always cooler than your skin, so your blood flow are cooler than your inner body, your core. So if there's more blood flowing towards the surface, what it does is that a little bit of that heat actually kind of radiates out into the air and cools off your blood in the process. So heat is really lost to your skin by a combination of radiation, conduction, convection, and evaporation. This is just an example of your blood flow, and when somebody is trying to conserve heat. So this person's trying to conserve heat. So you can see where they've really kind of constricted all of these skin vessels. So now they're trying to shunt most of their blood to their bigger, more core vessels. See how kind of everything's blue here on the surface? And that's because they don't want it near the skin, which is cooler than your core. Here's someone who's hot and trying to cool off, so now they're dilating all of these vessels so that some of that heat will be lost out in the air. So an abnormal body temperature, you can have a fever, and that is an unusually high body temperature, and that's normally associated with a systemic inflammation response. You should remember that from a previous chapter. And that's just because normally you have a fever because your body is trying to fight something off. Another example is malignant hyperthermia, and this is actually an inherited condition in which the body has extreme hyperthermia as well as muscle rigidity when it's exposed to certain anesthetics. It's sort of like a intense, very specialized allergic reaction, you could think of it as. So they just become extremely hot and their body becomes extremely rigid when they get exposed to certain anesthetics. And normally you don't know about it until they go in for surgery and have the reaction. So another problem that can happen that's related to body temperature is heat exhaustion. Heat exhaustion results from the loss of fluid as the body tries to cool itself down. So that's normally just from tons and tons of sweating. And normally this is accompanied by what's called heat cramps, or like cramps throughout your body, and that's just because you've sweat out so much fluid and sodium and potassium. So it's really disrupted your body's basic fluid and electrolyte balance. And then there's heat stroke, also known as sunstroke, and that is the overheating of the body resulting from a failure of thermoregulatory mechanisms in a very warm environment. So that means that your body maybe had been trying to correct or control your temperature and keep it within a normal range, but it just can't keep up. It cannot maintain your homeostasis anymore, so you suffer from heat stroke or sunstroke. You're just too hot and your body can't help it. And then there's the other direction, which is hypothermia, which is a reduced body temperature resulting from the failure of the thermoregulatory mechanisms in a cold environment. So that means that your body is trying to keep you warm, but it just can't maintain your the temperature your body wants to maintain homeostasis anymore. So that's when you're shivering and you're shunting your blood and you still just can't stay warm. Frostbite occurs in very localized tissues due to damage caused by extreme cold. So that would be that the environment is so cold that it's damaging your tissues, on top of the fact that you're shunting the blood away from that area. So it has poor blood flow and it's very, very cold, which causes a lot of damage to the tissues. And if it's bad enough, it can actually result in necrosis or even gangrene. So that's like kind of your tissues are dying and then they're like rotting away, which I know is kind of a gross thought, but that's pretty much what it is. And that takes us to the end of this chapter.